something,
They
I can
made
go,
you that you can.
I can make it go backwards for you. I can go
Okay.
back and forth.
So I mean, really what I'm doing is filling in some of the details of what I said yesterday.
Yeah.
So I'm not gonna give you all
The whole spiel, yeah.
No, that would be too long. Okay, so
Here, I'll make it go forward.
okay, so the idea, let me state it in kind of a general way, and I'll give you some very specific examples and tell you what needed to be done, and then you can see that the complexity of the problems that you're dealing with are orders of magnitude bigger from a computational point of view, but I think the ideas are much the same. So the idea is that over a certain period of time, you've made some measurements. And you have to choose, first of all, how frequently you make the measurements, and how many measurements you make. And I'll try to address both those questions. And the way in which we proceed is that in addition to these measurements, you have to have a model. It's really independent. It comes from what you discussed at the beginning yesterday. You have kinematic relationships, you have equation of state, composition relationships, and all those you have to somehow buy, and you have to have some way of verifying them either in a laboratory or through these dynamical methods, actually.
Yeah, that's
Okay.
what I find really
But
interesting.
you can't, I know this may sound obvious to you, but I've often been asked whether or not you can use what I'm going to be talking about to build the model, and the answer is no. No. If that were the case, we'd just get Mike over here to push a button, you'd have your model, and it'd be right. But that isn't going to happen. So let me,
Yeah, next.
oh,
It's easy saying do this stuff.
let's go there.
Okay, next.
All right, so this is just a way of thinking about the problem. Doesn't in any sense change the physics, but if you think about the data as having information in it and the model needing information, you need to determine parameters and you need to determine the state variables. In your case, the pressure at locations in space and time and the temperature at locations in space and time, where you don't have measurements because you need them as initial conditions for predicting forward. So you have to determine those as well, or you're not in terribly good shape. Anyway. Okay. And the reason that I say this is that one of the things that came out that rather surprised me is that you can quantify how important a measurement is in terms of bits of information it communicates to your model. So some measurements are unimportant. They communicate a hundredth of a bit per second, and some measurements communicate 10 bits per second. And how many bits per second you need is determined by the model, because nonlinear models where you can have chaotic behavior, which I'm almost sure must be true of your models.
Absolutely.
They are, one of the characteristics of chaos is it generates information. Well, it generates the entropy that you were talking about, to be precise.
Indeed.
Okay. So this is just established notation. I'll call the measurements Y. And I'll say they're capital L of them, and I'll call the dynamical variables X sub A. So A stands for discrete time space. It stands for temperature and pressure in your case, and if you have other variables, concentrations or this or that, they're all in the X's. So I just wanted to contract it into a shorthand notation. When you're all done formulating the model, you have to have an integration routine that tells you, if you tell me the state at this time, what's the state at the next time? That's what your complicated finite element tells you how to move ahead in time. And that's all I want to capture about the model, because that makes it fairly general. Okay, typically, both in smallish problems, and certainly in your problem, the number of measurements you make is far less than the state of the system. So one really important question, and we have some tools for examining it, but not for the detailed criterion is very complicated to compute. is to try to figure out how many measurements you need to make. And here's an unsolved problem that in your case I think will be important to think about. What if I tell you I need 10 to the 7th measurements and you can only make 10 to the 6th? How does that impair your ability to estimate the parameters in the states? And we have not thought about that very carefully. We've only worked over the methods where we have very good control over the measurements. So it's an interesting question to talk about, and I don't know the answer, okay?
Oh, you want? Okay, there you go.
Okay, this is just, more talk.
More time.
All right, so what I'm gonna do is tell you how to formulate the problem in what I'll call the worst possible but typical situation, right? You have noisy measurements, you have errors in your model, where you certainly don't know if they're right. Those errors can come from several sources. You just missed part of the model, you don't know it. In taking your PDEs and discretizing them in space and time, you of course get finite resolution, then there's always errors in that. And then there are numerical errors in the solution. There are always errors in the model of some kind. And furthermore, when you start your measurements, you don't know the precise state of the system. All you have is a statistical characterization of it. And you still have to estimate the state of the model at the end of the observations and the parameters when you're done. And there's an exact formulation for this, which I talked about yesterday. I'm going to show you today the exact formulation. And then I'll show you how we make approximations. There are many different kinds of approximations. All right, ready?
Okay.
Okay. So the notation I'm going to use is that the set of measurements you make during the period time 0, time 1, all the way up to time m, which means the end of the measurements. What you can expect to be able to calculate is the probability distribution for the state of the system. So that's the temperature and pressure in your case at all locations in x, y, z at the final time, conditioned on your measurements. If there were no measurements, that's what you do in your forward calculation, right? Start with an initial condition and move ahead. Okay, we're ready. So it's that probability. First, I don't know if you're interested in this. It's just a way of characterizing the value of an additional measurement. Suppose you have made 3 measurements, and I'd like to know what is the benefit to me for making this measurement instead of just the previous 2. So I go to my formula. It's the conditional probability of the state being whatever it is at time 2, given 3 measurements, and I want to relate that to the probability of the state at this time, just given the 2 measurements. And this thing in blue, this is just the identity on conditional probabilities. No physics, no nothing here. This is the mutual information as defined by Shannon. Mutual information between the state of the system at the time and the new measurement, given the previous measurements. Right? If you take the logarithm of this, you can express it in terms of bits, and if you take p log p and average, you can get bits per second and so forth. So in the next slide, what I've done is I've taken the logarithm. So this is the information you have after the 3rd measurement. This is the information you have after the first 2 measurements, and this is the additional information. It depends upon the model and the measurements, but what you're doing, therefore, by adding measurements is literally transforming information in bits, transporting information in bits from the observations to the measurements. And that seems kind of obvious, but this actually, and I'm going to use this formula now to give a general result, it tells you a quantitative way to say, okay, you made 100 measurements, should I make 101? Okay, you can answer that question. In your models, it's going to be very complicated, but I don't know whether it's important to you, but it could be.
I think it is. I
Yeah.
mean, knowing the value that you get from particular measurements and which measurements will give you the most information. is
Absolutely,
quite
that's the
important.
key question. I mean, the measurement could be a drill hole that you actually pay, say, $500,000 or $1 million for. So that's one measurement in the whole thing.
And is it worth it?
Is it worth it?
Yeah.
Yeah.
And I don't think at this stage, but maybe as you think about that in a really practical way, that you can decide that without a good sense of the model and the quality of the measurement.
Mm-hmm.
What you have is the location, where is the borehole, how deep it is, where are the instruments. And that all goes into that too, because these measurements, I've wiped out X, Y, Z, but that all matters. Anyway, so the general rule is that the probability distribution of the state after this sequence of measurements is related to the probability distribution of the state after one fewer measurement. And then you have your model. And your model can take the state at time m-1 and move it ahead with a transition probability to from the state at time m-1 to the state at time m. If there were no noise, if your model were perfect, that would be a delta function in your big space, because you know exactly, if I give you the state, your algorithm in solving the equations gives you exactly the state in the next step. It's not a delta function. So one of the things you have to do is make a representation of this transition probability.
Yeah.
And I'll come back to that. There are many ways to do it. The way we do it is we say, we have done it, is to say, well, most of what we've done to the model is reduce the resolution, either because of noise or discretization in space and time. We'll represent that as a Gaussian distribution resolution. If that's wrong, you can put in whatever you think is right. So the ingredients you need are the transition probabilities, so that you can go from your measurements here to your measurements here, to your measurements here, to your measurements here, and this conditional, the Shannon term, conditional mutual information, that tells you, you start somewhere, you move ahead, make a measurement, get some information, move ahead. So the formula is, frankly, very simple to interpret. Ready?
Yeah.
Okay, this just says it again. Do you need some help here?
No, no, I'm fine.
Okay.
Let's go.
We're waiting for you.
Okay. Go ahead.
No, to push the button.
Oh, I'm sorry, okay.
Do you have a button that I could push, Mike? That would save you from
Yeah,
tripping over
I
here.
think if you go, what's happening? It should work, but it's not. I mean, how this?
Wasn't that menu at the bottom?
Yeah, there used to be.
Yeah, no, let me just go. I'll just keep on doing it this way. Go ahead. Go ahead.
I think we want to go forward.
Did what go? Here?
Okay. So if you take that idea that you move ahead in time with your dynamics, acquire some information, move ahead in time with dynamics, you can now march through the sequence of your measurements. And what you find is that the probability distribution at the final time, given the sequence of measurements, is given to you by an interval with a probability weight function, and that's actually on the next graph, but I'll tell you what it is. It's the combination, of course, of the probabilities to move ahead at every step and the information that you acquire. So, ready?
Yeah.
Okay. I call this the action because it looks like a familiar formula from quantum mechanics, but it's a statistical physics formula where this is playing the role of the Hamiltonian in the formula e to the minus h over kt. That's all. So kt's 1, and this is like the analog of the Hamiltonian. So in that sense, the probability, transition probabilities from the state at time n to n plus 1 is like the differential equation or the Hamiltonian that moves you ahead. This information acts like a potential in the following sense. If you have a distribution of initial conditions, your equations of motion will take them all throughout the state space wherever they go. But the measurements say, by the way, you're not over here, you're here. So it acts like a potential to guide your solution to where it should be. And that guiding will be better if you have good parameters and a good sense of the state. And that's the information that you get. So you guide the system through the state space during the measurement period, and that's what that term is explicitly doing. Okay. Next. So now, what you can get from these probability distributions are expectation values. You can either get moments, or you can get marginal distributions, or whatever you want. And any function on the state of the system, and I call this a path because it's the state of the system at time 0, time 1, time 2, so it's a path through your state space. Any function on that path can have an expectation value, which means doing this interval. Okay. So that's the essential thing you have to do. If you would like to know the expected value of your temperature at this location at a sequence of times, then f is that variable, and you do the integral, and your job then is to estimate the weight function in the interval. Okay? That's the job. For you, capital X, if you have 100 times and 10 to the 7 state variables, is 10 to the 9th dimension. So it's a fairly big interval to do. And I told you that I don't know how to do such big intervals, but in principle, they're methods. All right, ready? Okay. The way I know several ways to do those intervals. Oh, you want to go back one, please? The ways that I know to do the integral are to do an estimate using are you familiar with Metropolis Hastings Monte Carlo methods?
Yeah.
Okay. No?
I mean, not that much, but...
Okay. What they do is they say, you're in a high dimensional space, the space of capital X, which is this path. And you want a distribution of points in the space that are distributed according to this exponential, which you know. And I'll show you the explicit form of it. So the way it works is you make a guess as to what a good path is. And then you perturb it. And you use a procedure that weights your decision according to the probability, e to the minus a0. And you either accept the new path or you reject it. And you do that many times, collecting all the paths you accept, and then you average over all those paths. All right? I mean, it sounds simple, but it's a brilliant idea that was invented in the 50s by guys building nuclear bombs. What can I say? Right? It's been applied to more peaceful things since. And that's commonly used in statistical mechanics. We didn't invent that. And there are many methods out there that you can decide how they fit your problem. All right. Oh, I'm sorry, one back. The other way that I know how to do integrals like this is basically a Laplace's method or a stationary path method. So you look for a path along which the weighting function is stationary, and then you do a Gaussian approximation in the neighborhood. Okay, I'm going to talk about both of them. First the Monte Carlo method, and then the stationary path method. Turns out in complicated nonlinear problems, it's tricky to do the stationary path because of chaos. Because the stationary path implies a kind of regular, smooth in particular, passage through the state space, and you have to regularize the state space in order to do it. And I'll show you how to do that. All right. Am I going too fast?
No, that's fine.
Oh, okay. This just gives a bunch of methods that we've tried on doing the integral. We ended up doing the Metropolis Hastings, which, as I said, you can find in dozens of books. You can find codes written for it. And we wrote one of our students just wrote a C code. It's only about 30 lines. This is not complicated.
Yeah,
We do. It just takes a long time to do it. Okay.
And I understand you have actually imported it on a graphics chip, is that?
I'll come to that. That's right. Look, when you're doing the Monte Carlo methods, you're doing, as I said, you take a guess as to a good path, and then you perturb it, and you select it or don't select it. Well, you can do that in parallel by taking a path and randomly perturbing it on every possible process you have, There's no communications necessary. So you don't need all the really nice communications stuff that you probably have in your 10,000 or soon to be.
Finite element, we need that, yeah.
That's right, but you don't need it in this calculation because they're all independent.
Yeah, no, I
So
see
you
that.
can do 10,000 paths at
Yeah.
once.
But
Now that's, you have an expensive way to do 10,000 paths. And in a GPU, you can do hundreds of paths for $200.
Yeah, that's right.
on the basis of what you actually select one of the paths?
Well, you have to have a good guess,
Yeah. That's
and then you start
good.
perturbing in that neighborhood.
Yeah. And
So,
then,
suppose your exponential up here were a Gaussian.
yeah.
Well, one good path is the minimum, because that gives you the maximum probability, right? But that doesn't tell you the whole distribution, and what you want out of this is not just one path, but you want statistics. You want a mean value, and you want RMS errors,
Okay.
and you want RMS distributions on your parameters.
Perturbed, yeah.
Okay,
Yeah.
It depends on actually some of the moments you could know or something. Right?
that's right. How you guess your first path, it's an art. Okay, I'll tell you how we do it.
And how you perturb the path is an art too.
The specific way you perturb the path is an art as well. We frankly just use good old 1950s Metropolis, well, Hastings was 1970, Metropolis Hastings, which just says, add a little bit of uniform noise to each element of the path. There are probably many smarter ways to do it. If you have 10 to the 9th
Yeah, if you're
degrees of freedom, you better be as smart as you can, right?
Yeah.
But I don't pretend to know how to do it best. I know how to do it
Yeah.
okay. All right. Let's go on. These are just... So now, here's how we approximate this action. First, if it's true that the measurement at one time and the measurement another time are independent, you can use that to simplify that mutual information. And if the measurements have Gaussian errors, Gaussian noise in them, which is probably typical of your
Yes.
measurement devices. Not all measurement devices do, but then this simplifies into just some of the comparison of your observations and, it is working now. This, this simplifies into just the least squares comparison of your measurements and the output of your model.
Yeah.
So that's the measurement term.
Okay.
I said if the transition probability is completely deterministic, it's just a delta function in your state space. If you're here, you know exactly where you're going. But with noise, this sigma just represents a resolution of the size in state space, which I've represented by a Gaussian. When you do that, the action, the weighting function in your integral, just becomes this least squares comparison of the model with the data and some smoothed out, slightly broadened distribution of locations in state space. This action is not linear, not quadratic. This term is quadratic, but if the dynamical function is nonlinear, as it is all over the place in your equations, the second term is not quadratic, so you don't have a Gaussian interval to do. It's much more complicated. But when you're doing the Monte Carlo calculation, it doesn't matter. And in fact, in the Monte Carlo calculation, it's easier. I think we mentioned this. It's easier than the forward prediction because you can use a nice implicit form for your stepping, but you never have to do the Newton-Raphson
Yeah, you mentioned it. I see that.
Yeah, exactly.
calculation, and
Yeah,
because the xn and the xn plus 1 are just two elements of the path, all along the path. And you simply adjust them independently to minimize that thing. And the Metropolis Hastings method does that automatically. Okay. So what are the parameters that enter here? This RM is basically 1 over the RMS error in your measurements, and 1 over RF is 1 over the resolution error in your model. So that's the approximation of this. We've checked out all sorts of other distributions. Lorentz distributions, 1 over 1 plus x squared to a power, check out gamma distributions. You can do anything you want. And it's not a the computational complication is nothing from one choice to another. So if you happen to know that an instrument puts out Poisson noise,
Yeah,
no problem. Just, you have to know that, it doesn't know it. Okay, ready? So here's, I'm going to give you some examples. This is an example that was invented by Ed Lorentz, the guy who found chaos almost 50 years ago. It's a long time. And his idea was to mimic fluid dynamics by having quadratic nonlinearities and damping, the viscous term, in one simple forcing. So these are just points on a circle. And it's known that as you turn up the forcing there, you get first fixed points and then limit cycles and then chaotic behavior. And we looked at various dimensions all the way up to 100. Well, that's on here. We've done 500 and 1,000, but we didn't learn anything new, so I don't present it. Why don't we skip the next few, because mostly I'm talking about how you can, go ahead. More. Okay. I can go back to that if you want, but by looking at the structure of this action as a function of the number of measurements, you can get a sense of how many measurements you need to get a good estimate. And what that shows is that if you have too few measurements, the action is very complicated, and there are many minima in that big space. But as you make more measurements, and I think this goes directly back to what I was saying, where the more measurements you make, the more you are guided along the right path, that action simplifies, and the calculation actually becomes more accurate. But now I'm going to show you what happens for some explicit calculations, and to show you how you could get things. So I'm going to talk about a 20-dimensional system. And we know from a variety of calculations that we need 8 measurements out of the 20 in order to estimate the other 12 and to estimate the parameter. I'm going to give you the distribution of the parameter that comes out, and I'm going to give you the expected orbits plus the RMS error. In our case, because we are doing what we call a twin experiment, we know the right answer, so we can compare the outcomes. Ready? Okay. So the black line through a region of arbitrary units 0 to 4 and through a region 4 to 6 are the correct answer that we calculated beforehand. We gave the model 8 out of the 20 variables. One of the ones we gave it was the 0th. And, to the data that we gave to the model, we added noise, which was just Gaussian normal with a signal to noise ratio of about 20 dB. So what's that, about 10% noise? So it's not a lot, but it's enough.
So you're moving around on what, an 8-dimensional attractor is what you're saying?
No, the attractor.
You said there are eight positive Lyapunov exponents, right?
Those are the conditional Lyapunov exponents of the stability, the synchronization between the data and the model.
Okay.
The model itself has probably a dimension of about 18.
Okay.
I actually never computed it, but I know it's close to the number of degrees of freedom.
Okay.
This is really a very complicated, chaotic thing. You can see the blue dots, which is what we gave the model, deviate from the true values, as they should. They're noisy. What comes out of the interval that I described is the expectation value and the RMS error. And you can see that during the observation times, it actually matches extremely well with fairly small errors. And we need this quantity plus 19 other state variables plus the parameter in order to predict into the region where we have no measurements. So we have those. We use that to continue that interval, because if you take away the measurements, it just predicts for you. And so here are the predictions. The green is the predictions, the black is the correct answer, the red is the RMS error. So you get, really you get the statistics out of this, not just a single answer. So that's kind of nice. And the deviation of the green from the black, especially as you go forward, will be bigger and bigger because it is chaotic. And any error that you make here gets amplified.
Does it go exponentially in terms of the deviation? Or
Well, what happens is that exponentially the deviation grows from being small to as big as the attractor is in the state space. And then they move around, they never get exponentially different from each other because the motion's bounded in the space.
Mhm.
So in their case, the temperature will not go to infinity.
Fortunately.
Well, which would simplify your problem, right?
Yeah, it's only happening in Tokyo. I mean, Japan.
Okay, so the next picture we asked, in the region of measurements and in the region of prediction, what is the skewness and kurtosis of the distribution of states? In other words, is a Gaussian assumption good? If a Gaussian assumption is good, you can go back and do a lot of things much more accurately by hand. And in this problem, it's very good. I'll show you in other problems it's not so good.
Well, why does the skewness and kurtosis blow up in the prediction area?
Because you no longer have any guidance. All of your points are simply moving onto the attractor, distributing themselves around the strange attractor. The strange attractor is absolutely not Gaussian in the state space. Think of the Lorentz attractor. No Gaussianity about it, right?
Yeah, so it's a wrong assumption.
So it's doing exactly what it should do there. And those are just moments of a complicated distribution, which are not Gaussian.
I know that it's almost a diagnostic that things are breaking down in terms of your predictive
Well,
capability.
yes, exactly. Okay, next slide is the same calculation, but with a not observed variable. It's not so hard to get the observed variables because, after all, you observe them, right? But the unobserved variables are the challenge. And I don't put on any blue dots here because even though I know that the black is the right answer, I didn't present that to the model. It still tracks it extremely well in the observation region. And this value is one of the ones we need for prediction, and there's the prediction of the unobserved variable. Kind of sounds like magic, but it's not. What's going on is that your model is acting as a nonlinear filter because the observed variables interact with the unobserved variables. And because you require your model to be satisfied within a certain resolution, it forces the unobserved variables to satisfy the model within that resolution.
Sure.
Okay, so it's not magic, it's just magical.
It's surprising. Yeah.
Okay, you can see that on the unobserved variables you get a little bit more skewness and kurtosis, and it does the same thing.
Fortunately,
Okay.
yes.
Ready?
Yeah.
I don't remember exactly. You can also, because, remember I said that the method is you propose a path and you select those paths that give better samples from e to the minus a0. That's how the method works. So once you have a large number of paths, you can just go in there and say, make me a histogram of that variable, or make me a histogram of that variable. So I'm going to show you what the marginal distributions look like. This is a variable totally selected out of my head from d equals 5. And you can see it's not Gaussian, but there's a distribution. And if this were the temperature at that location and you want to know what was the probability that it was above a certain threshold, you can just integrate that histogram and get that probability. So you can, when you come back to your risks, that information is extractable from here. Next. This is the probability distribution on your parameter. The correct value, the value I put in with no noise, was 8.17. That's the peak, but now I come to you and I say, you had a permeability of this kind of rock. I'm going to give you a value plus or minus some errors, which I think is a better characterization from a physics point of view than one number. Okay. And so you can get all of those numbers out as well. I forgot what the next one was. Oh, I just show you that as you increase the dimension of the problem, it becomes less and less Gaussian.
Yeah.
Maybe we're not surprised. But I didn't say this on Tuesday, but when we submitted a paper on this, one of the criticisms we got was that you guys use only 20-dimensional
Yeah.
system and everybody else uses 40, what's wrong with you? Really, I swear, we got this. And since we had done the 40 and we didn't learn anything,
Yeah.
I wrote back basically saying, okay, you think we're wimps, so we're going to do 100. And they accepted the paper immediately.
All right.
Right. This is a different question. This is the question where I make measurements in a certain interval. Every time I make a measurement, I make 8 measurements in this case. And now I ask, what happens if I make measurements less and less frequently? So I start taking away measurement times.
Mhm.
How well can I still get an accurate answer? And in the little squares on the bottom are estimates of the error in the prediction. And you can see that you do very well with a lot of measurements, you still do well with fewer measurements. You come to some point and you just fall off a cliff. And so this is a way in the model of telling you how frequently you need to make measurements, which is probably also a practical question.
Very, very important. Because
Right.
we need to basically assign that in advance for our
Right.
basically layout. So
But now this statistical method allows you to say, oh, it says here I should make 20 measurements.
Yeah, yeah.
I'm going to be careful, I'll make 30. But I don't have to make 80.
yeah,
And I mean, it goes, I mean, the way I interpreted this, Henry, was that, you know, there's a information sort of transmission that's coming from the measurements, and it's sort of consumption that's in the problem. And whenever there's a particular, you know, this looks like there's a real threshold behavior,
Right.
is that you need to go and be making enough measurements to sort of outrun the chaos. But
That's exactly
as soon
right.
as you can outrun it,
Mm.
you don't need to go any further.
Right.
There's no real value. There's no value if you're below it, all of a sudden there's huge value, then there's no value in
That's
increasing it anymore.
And as I said to Klaus, even though you look here and see that 20 are right,
yeah.
if you were designing something, you'd put in a little safety factor.
Of course.
Yeah.
Yeah.
But what Mike said is absolutely correct. Another way to look at it is, you know, if you make no measurements, you have very little predictive value, okay? And so somewhere between no measurements and a lot of measurements, you've got to do well. And this is a way of quantifying it.
And also, I mean, that can be dependent upon where you go and make the measurements.
Oh,
It may well
absolutely.
be an entry production at one point or one part of the space is greater than entry production at another part of the space, and you want to have a higher density of, or you know, the threshold is going to be much higher in the area of higher entry.
Absolutely correct. In this simple model, it sits on a circle.
Yeah.
You don't see that kind of detail,
Yeah.
but you're absolutely correct.
Yeah.
All right. Oh, sorry. You ready?
You know, for us, then that means you put the wells where it's the greatest entry production
Yeah.
in your physics.
Yeah,
That's right.
sure.
Because that's where you're generating most uncertainty due to the other one.
Mhm.
All right, this is our we're not wimps picture. It's
It's 101.
That's right. You really don't learn anything new except that you. So you might say, all right, how long did it take to do the Monte Carlo calculation for d equal 100 versus d equals 20? D equals 20 took 20 minutes. D equal 100 took 25 minutes on a CPU.
That's good.
CPU. In other words, there really isn't much difference because the fundamental thing is perturbing the path and choosing. And perturbing the path is trivial. And choosing takes a little comparison of that, but you're comparing scalar numbers. The action, you're not comparing all the components. Okay. Here, again, the skewness and kurtosis, you can see in high dimensions. It's not, I wouldn't make a Gaussian approximation, but I don't have to. But if somebody says, why don't you? You can come back and say, oh, this is why, or good idea, wish we'd thought of it, and here's the back end. Okay. So here's what we found using GPUs. So what GPU did we use? We used first the video card in one of my students' 3-year-old Mac. And we used a code from NVIDIA called CUDA. I don't know if you're
Good, I know,
familiar.
yeah.
So he learned enough of CUDA to be able to distribute these Monte Carlo calculations. They got a factor of 100 speed up in an afternoon. You can imagine how excited he was. We gave him a PhD also.
That's nice of you.
Thank you. And now we've done a lot of different, detailed different ways of distributing the problem. We found that you typically get 60 to as much as 200 times speed up, depends on the NVIDIA board and so forth. We've also demonstrated that if you take these problems and distribute it over many NVIDIA boards, there is a little bit of communication loss from board to board, but we were getting 95% of the number of boards. Yeah, it was pretty good. And we're about to do the experiment of buying several boxes and using InfiniBand, InfiniBand communications to limit the loss in communication time to see if we can continue to get a high fraction of the number of boards. I noticed, what was his name? Lawrence Murray, who works over in the other part.
Florian.
Is
That way. Is that way?
I think it's the other way.
I don't know.
Doesn't
That
matter. Probably not there. Or not there.
Anyway, he's worked with your GPU cluster here,
Yeah.
and he says that they also, on completely different problems, much simpler, see significant speed ups on the Monte Carlo calculation, not on the forward integration of PDEs. That takes the other kind of machine. So there's some interesting work to be done here in calculations. The problem with the GPU boards, from my point of view, is they generate an enormous amount of heat.
That's true.
So you don't want to use them in February here. But they're very interesting and promising. We also did the following experiment that you might be interested in. We bought 2 GPU cards and bought a box with a lot of fans and built our own. One of the cards was just the standard gaming card that in the US costs $200. And the other was their fancy Tesla card that costs $2,000 in the US. The gaming card worked a little bit better on these problems because there was a little overhead because of the floating point unit in the Tesla card.
Well, what? I mean, why would you ever get the Tesla? I mean, are there people that are really upset that the Tesla is that much better then? Or?
Well, if you wanted to do the forward integration on the GPUs, you might need the double precision.
Okay.
Right. The other is NVIDIA they're not dumb people. They only support the Tesla card for scientific computing. Their Tesla card is exactly the same as the gaming card. It has the floating point unit disabled on the gaming card, and they charge 10 times as much. So that's their business model.
So you can probably do this, undo this, and enable the whole thing.
According to this Lawrence Murray, very interesting guy. I thought he was a good catch for you. They have only the expensive Tesla cards here. So that shouldn't slow you down too much.
That's okay.
All right. Anyway, so let's go on to the other way of doing these integrals, which is to look for the stationary path through the, you know what I mean by Laplace's method?
Yeah.
Okay. Amazingly, not everybody I talk to does, and I didn't want to. So the question is, how, given the action, can you look for extremum of the action? Okay. So I'm going to talk about doing problems similar to the one I talked about in the following circumstance. I have noisy measurements, but I have a very high resolution dynamical equation. So what I'm going to do is try to minimize the information transfer subject to the equations imposed precisely. Right? And now I'm going to show you what happens if you try to do that. All right, so we're back to the Lorentz model. And so I'm going to talk about a 5-dimensional model. That 2 is a 5.
It doesn't matter, yeah.
All right.
It goes back to 2.
And by fooling around with this, we know that you need 2 measurements in this case. So what we're going to do is look into the cost function, the difference between the model output and the measurement squared, the least squares determination of that, as a function of the strength of the coupling that we use to bring the information about the measurements into the model. So we can go to the next picture. And I want to show you what happens as we vary the strengths of these couplings, and to show you what happens to the structure of this as a function of one of the things that you want to determine, and here it's the one of the initial conditions. Exactly what I show you is true for the parameters as well. Okay, ready? So this is the cost. This is just a calculation directly from the model as a function of one coupling, function of the other coupling, and this is the quality of the match between the data and the model output. You can see with your eyes that this is 0, so this is a good match. And when you have 0 coupling, because these are chaotic, you have a terrible match because the model output is chaotic, the measurement's chaotic, and they're incoherent. So, ready?
Mm-hmm.
So I'm going to show you what this cost function looks like at these 4 points as a function of that initial value of one of the state variables. Okay. So the first point is 0, 0. And if you want to determine that the initial value of this state variable, the second one, is what I know it to be, 4.9, you have to invent a search across this surface. And I don't think it's possible. Not the least of which is that the minimum isn't even at the right place. All right? Now we go another place. This is when one piece of information is coupled in. It's the same problem. This next picture is with the other piece of information coupled in. It's the same problem. And the next picture is with those 2 pieces of information coupled in. And you can see that by bringing in that information, it guides the orbits to where you want. It makes the data and the model coherent and gives you a nice smooth search curve. I'm going to show you the same thing happens in an experiment we did with a chaotic oscillator. So here's what we do to do that minimization. This cost function is the information transfer function in the action. What we do is we couple in information about the data to the model with just this simple coupling. There are many other ways to do it. This one works. We have it all coded up so you don't actually have to think anymore. Got this working. We make the coupling a function of time because the instabilities in a chaotic system vary around the attractor. If you think of the Lorentz attractor, it's very unstable at the origin, but very stable as it moves around here. So in certain regions you don't have to control the instability very much. This automatically controls the instability as needed, and you pay a penalty for the cost of the instability in this U-squared term. So the way that the optimization works is you start off, as in any optimization, you start off with a guess. Then you have a routine that gives you one iteration, and then another iteration, another iteration. It works very hard to synchronize the model output and the data. And when it's doing a good job of that, it minimizes U squared and gives you 0. And I'm going to show you how it works. All right. So this is the circuit. I already told my jokes about the circuit, so I'm not going to tell you.
We haven't heard them.
Oh, okay. This is a circuit called the Colpitts Circuit. It was invented in the 1920s by a Britisher named Colpitts. Mr. Colpitts did not have a bipolar transistor in his circuit. But these days, almost everybody has a Colpitts circuit. Here are the keys, the car.
The Colpitts in there.
Yeah, you push this and it opens. It's a little Colpitts oscillator in here.
Oh, right.
They're so cheap, they're throwaways. Anyway, we built one. The other joke is that the circuit we built cost $10. It cost $5 for the power supply, $4 for the parts, and $1 for the discounted labor of the graduate students. Okay. Sorry. Anyway, here's the circuit equation that's put into dimensionless form. And now, as a function of the coupling of the observations into the model of the circuit, I'm again calculating this cost function, and I'm going to fix all parameters except this one, and show you the same thing happens, first of all, in this calculation and in the circuit measurements, as I showed you before. Ready? So this is no coupling, and this is the number of terms in the, it tells you how far along you go in the time series, how well you explore the chaotic behavior. As you start off in the time series, all you see is a little piece of the waveform, everybody looks the same, then the chaos sets in the waveform. So now you have to search on that blue surface for the minimum that I happen to know occurs at 6.3. Isn't going to happen. Next picture. I turned K up a little bit, so they're not quite synchronized yet, and you still have a search problem. But then I turned it up to about 2, and you see this same feature, that you've regularized the search problem, and the search clearly gives you a number in the neighborhood of 6.3. Okay. Here's how the optimization procedure, this is the outcome of it, but I don't want to bother with this. Let's go on. Next. Next. Okay, what I'm going to do is show you the optimization procedure, minimizing that least squares match between model output and measurement. I'm going to show you first after 6 iterations. The initial choice was that all of the variables in your search are just constants. So it's starting to search, we present it with information on the black line, and it's busy trying to match the black to the black, the green to the green, and the red to the red. So the black's getting there after 6 iterations, the green is really bad still. And if you look at the next slide, this is how big that coupling parameter is over the observation time. It's big, because you started off with a completely bad idea of what the right answer was, and it's pushing you towards it. All right.
But again, how do you, what sets or determines the size of the coupling parameter as you're doing the optimization?
Let's go back to the, a little bit more. So, what you're doing is, no, it's not here, back. What you're minimizing is the error between the model output and the measurements plus u squared, minimizing this. This minimization problem, you have to give a guess for the states, a guess for the parameter, and a guess for the u when you start. And it adjusts it during the minimization, searching around in that space. And what the values are at an intermediate stage of the search, you don't care.
But it's part of the minimization.
It is exactly, that's right. You enlarge the space in which you're doing the minimization. And you can think of the coupling just as a constant at every time point where you're making the measurement. There's no dynamics to it. It's just a new constant, and you're trying to pick that constant to minimize that cost.
Gotcha. Okay.
So, next one is the size of the u at that stage.
Okay.
Next one is the picture of the states after 22 iterations. And you can see it's doing pretty well here. Still, it hasn't gotten the blue ones at all yet. And the U at this stage is the next picture. And it's still kind of big. And you can see it varies enormously across the attractor. In this region, you don't need it because it's small. Right. Okay, then if you run the optimization routine...
But if you were looking at this, wherever the particular regularization is large, it's an indication of large entropy production. And if you were to go and try to optimize data acquisition, you'd be wanting, if you were sort of going through this process real time, you'd want to go and start putting your measurements where there were high degrees of regularization.
This is the middle of the optimization procedure. You want to look at it at the end.
Okay.
And at the end of the optimization procedure, if any of the U's are still big, then you better go focus on the quality of your model there or the quality of your measurements.
Okay.
That's exactly right. This is the end of the optimization procedure. You give it, you give it an initial guess, it does its routine, and it gives you a final answer. You give it limits. You want it to be accurate to a part in 10 to the 5th or whatever. Anyway, all of the variables, both the measured and unmeasured state variables, are really good. And the next picture is the U, which you'll notice is 10 to the minus 13. It's 0, because this is within round-off error. So
But I
in
mean,
this
that
problem,
being said, though, I mean, it is that round off error, because right now, this regularization is controlling the entry production from the round off error.
That's right.
Calculated.
this is a signal to you that everything is good in this problem.
Yeah,
But think of the following problem.
but it has a real practical numerical result, is that it's keeping the solution from blowing up because of round off error that it becomes.
No, the solution doesn't blow up because the dynamical system, the dynamics is dissipated, so all points just stay in a finite region of the state space. This is telling you that the model and the data you gave it are consistent with one another. You don't need this U to control. But you can do the following experiment. Take the data from the Colpitts oscillator, and I'll show you data from the experimental oscillator, and present it to the wrong model. Then the only way in which you'll get the variables to match up is if U is big, and you'll see, you won't see U equals 10 to the minus 13, you'll see order 1. And I think I have a picture of that later. So here's the experiment. Oh, I'm sorry. The three dynamical variables in this simple little tank circuit are the current through the inductor, the voltage from the emitter to the base, and the other one we chose was the voltage from the emitter to the collector. Okay. Next picture. This is that same picture of a cost function, a match between the data generated in the experiment and the model as a function of one of the resistors in there. And you can see there's a universal minimum here, but this is the surface over which you have to do the search, and unless you know the right answer, you're never going to find it. As you couple them together, the surface gets smoother, and the minimum remains exactly where it is. And so, systematically, during the optimization procedure, U gets big where it needs to be, regularizes the search, allows you to do it, and at the end it gets turned off. So here is the observed data out of that circuit that we built in red. The black is the estimated observed variables. These are estimated unobserved variables. We then took the values here at 10 milliseconds and the values for all the parameters, and we predicted ahead, and that's in the next picture. So we predicted ahead from 10 milliseconds forward in time. You get very good predictions until, because there are no measurements being made anymore, the chaos amplifies the small errors in your estimates here, and you can no longer predict. All consistent, works in an experiment as well. Okay, why don't you turn it off? This is another.
To turn off.
Yeah, I'll just say some words about this. You can go one forward, I think it's blank. No, it's a summary. Okay, one forward more is good. So, you can use this in several ways. Let me talk about two of them. One of them is probably kind of important for the kind of things you're doing, although I've never done it in a problem with as many variables as you have. When you make a model, you include all the terms you can think of. Some of them are irrelevant. This method, when you present data to a model that has more couplings, more degrees of freedom than you need, chooses those couplings to be 0. So it takes a big model with extra dynamics and prunes out only the parts you need. It's kind of nice that way. It doesn't add anything when you're missing it, but it takes away things that you don't need.
That's good, yeah, that's fantastic.
Another way to, and now this is the other subject, another way to think about the control, and in your problem, the control, that's U, will be a function of X, Y, Z, and T. So it'll be operating on all of your state variables as they move through this, your complicated state space. If at the end of the calculation, one of these controls is still big, it tells you that in that region of state space, and at that time when it's big, the only reason why you're getting a good answer out of your model is because you're being forced to it by the data. And that tells you where to go fix your model. Because it says the dynamics in that region isn't matching your data. It doesn't tell you how to fix it. That would be too much. But it tells you where to go. That's really the end of the story. I mean, we have lots of stuff here and there.
Well, I was interested to see you had actually you said something about extreme events in there. How is that model actually?
The Monte Carlo method gives you the distribution of any variable you want. How accurately you can capture the tail depends on how many paths that you choose. I mean, if you have a distribution with a far tail, you may have to do a lot of calculation to get a tail. If that's important, you can focus on getting the tail. The way I would do it is that there's a analytical characterization of extreme events, and what I do is get the Monte Carlo calculation to give me the parameters in that analytic form, rather than try to get the distribution itself. But I haven't done that yet. I mean, there are many things here we haven't explored yet.
But there is right now this hope in actually using basically overcomplicating the physics of the problem. So starting with a model where we actually throw everything into the kitchen sink,
Right.
model, and then just really see through the dynamical data, weed out the unnecessary components.
Right.
Yeah.
So the way I would do that in practice,
Yeah.
before I'd go to the field data, is I'd do some of these twin experiments, where you say, I threw in everything including the kitchen sink,
Exactly.
right? And then I presented it data without the kitchen sink, and I want to make sure it says you don't need the kitchen sink.
That's fine.
Then I'd be confident to go to field data, because you
Yeah,
have much
yeah.
more control over these twin
That's right.
experiments.
That's right. Yeah, that's good.
You also have to work out how you do the numerics in a controlled way, not on the data in the field. I wouldn't do it that way. But so I've told you pretty much where we are. We know how to do problems of order 10 to the 3, 10 to the 4 degrees of freedom in a practical way. So it means interesting calculations take half an hour.
With a reasonable size computer, and do you have hope to be able to get up to these 10 to the 6th, or?
That's our goal over the next couple of years, is by using sequentially bigger GPU machines and maybe some smarts on how you do Monte Carlo calculations that we don't know yet. Our goal is to do about 10 to the 6th degrees of freedom. But we are not, we're not that good in doing computing, frankly. We're not so clever. So if we could get some good ideas from you or the people we work with, we would be thrilled.
Yeah, we'll have to basically develop for the current POSI supercomputer that is being installed. And there is actually a number of graphics chips as well installed on that one. So
Is that right? Do you know what the complement will be?
it is not exactly, I mean, you
Yeah, I mean, that's really an open question.
An
And
open
I think I
question.
told
It's
you that we have
asking
these
for
two prototype systems. The first is the standard sort of, dual 6-pack CPU type machine. The second one is going to have a significant amount of GPU on each one of the nodes. It's going to be VWA. And we're sitting back right now asking which of the two architectures, or do we do 50-50 on the larger machine going in. But that has to do a lot with problem mix,
Right, absolutely.
and
That's
versus,
right.
I
the
mean,
astrophysicists are right now sort of in the first call, so that since 25% of the computer is being assigned to astrophysics, they will basically have the first call for the square kilometer array. But apparently geoscientific computing also has 25% assigned, so dedicated, so there will be 25,000 cores for geocomputing available, and you're probably speaking to the people who are going to are expected to run these cores. So it's for us it's more of a problem actually how to give meaningful tasks to these things, because there's no big investment in actually people at the moment to come up with some decent problems. So I think a problem set that we'll be looking at will be basically pretty much to find the geoscience computing. Then there is nanochemistry as well over this molecular dynamics solvers and so on.
And I think that we're, in a way, also ourselves struggling, because we know that some of our forward models are going to be, implicit, and you
Yeah.
may end up demanding a lot of communication.
A lot of communication.
Where, we know that other parts of our problems are these
Mhm.
metropolis-like things, which are very low communication, and because of that, work very well and parallelize very well. But it's really sort of the tension of the mix also means something in terms of the architecture of the machine that you
Absolutely.
want.
Yep.
So. And also, especially with Klaus and Ollie, they are using a lot of implicit solvers, which are
Yeah.
very communication, intensive
Yeah,
type
yeah.
things, and have problem scaling unless you really sort of have mega nodes. So.
Yeah.
So I would do two things. I would take the class of problems you're interested in and coarse grain them significantly
Yeah.
enough
Sure.
and see how much gain you can get doing
With-
it on GPUs versus CPUs.
Yeah, yeah.
The other thing I might think about is actually solving even the forward problem using this method,
Yeah, that would be interesting. Yeah.
accepting a certain loss in resolution
Yeah. Yeah.
instead of the commitment at the time to do the inversion for.
That would be very interesting.
This I truly can't tell you where that would go,
Yeah, yeah.
but I'd give it a chance. I mean, if,
Yeah, there's a.
Can you expand a little more? I've heard you say it a couple of times in terms
Right.
of using this method in order to, reduce the
Right.
the resolution
well,
requirements.
let's go back to, I don't know where to go. Back.
Okay. Oh, you want to go way back in the presentation?
Yeah, near the front maybe, and then go forward.
Let's see. Just escape button. This is one that's in trouble behind it.
Well,
Let me get rid of this.
okay.
So here we go.
Yeah,
Okay.
that's the one.
Yeah, here it is. Now it's opening another version of it.
Yeah.
As soon as it gets open.
Always good to have another version running.
I'm sorry. Don't say. Okay, we're
I don't know how far,
There.
go down. No, back,
there.
one more.
One more.
No, I guess you have to go forward if you want, sorry.
Just to
There.
That one.
Okay. This is the dynamics.
Mm-hmm.
Suppose what you have here is you've cast your PDE into an implicit high order solver to be able to move forward in time. That means that given the state xn plus 1 appears over here on the right hand side too, and in order to proceed you have to solve this nonlinear equation at every step in order to get xn plus 1.
Yep.
If you're willing to give up a little resolution,
Makes
what you
sense.
do is you have to evaluate the right-hand side always, but you don't have to do the nonlinear solver part to get xn plus 1 from xn.
What do you do with the xn plus ones on the?
Now this, if I had a, I know I can write on this, right?
Yeah, well, go here. Well, actually, right now you can write on it. Go right. Right.
Okay. This guy,
Yeah.
oh, look at that. Becomes some g of x of n, x of n plus 1, and the parameters.
Mm-hmm.
Right, this is now the implicit solver,
Yeah. Yeah.
right? You give me xn, in order to get xn plus 1, I have to solve this nonlinear connection between them.
Yeah.
Here, I don't have to do that. All I have to do is present to you a path. That means I give you a value for x1, x2, x3, x4. I just plug in those numbers. It requires evaluating this vector field, which can be expensive. And then I calculate this scalar number and compare it to the scalar number for a previous path.
Yeah.
And I say,
Yeah.
do I accept it or reject it according to Metropolis Hastings? So I've given up a little bit of the resolution. It depends on how big that number is, and you can fool around with that. When RF goes to infinity, this Gaussian term becomes the delta function. But when RF is large but finite, you accept some error in here, and you don't have to do that inversion. And if that is costly in what you're doing,
It is very costly in our systems.
then you save all of that
Yeah.
at the cost of a little resolution,
Yeah.
and what you get out is an expected value instead of a precise value, plus an RMS error, which reflects probably what's really going on in the probability. That's what I'm saying.
It's pretty cool, isn't it?
That's really nice.
Klaus?
Yeah, that's really good.
For us, it hasn't been a big deal because we have such low dimensional problems.
All right.
Yeah, but for us, when we have
we
high
don't.
dimension and highly implicit,
Yeah.
Oh, then it could be the whole
Could be the whole
wax.
game, yeah.
Could be the kitchen sink.
We could try it in as
We
well.
threw it out, but now we're throwing it in.
You're right. Yeah, that's what people always say about
So-
it.
So I really, I don't want to pretend I know how to do all these
Yeah,
high
yeah.
dimensional problems.
Yeah,
All
yeah.
I'm saying is this has worked extremely well on problems up to about 100 or 1,000. And I only see numerical issues proceeding, and I'm not really good on those. I'd like to become better, but I'm not really good on
That's nice.
okay. Any more questions you guys have?
them. Yeah, what's the right answer? Yeah,
I
sorry.
mean, is there ways, I mean, does it make sense to sort of build off of some of the program infrastructure you have, or does it make sense for us just to roll up our sleeves ourselves in terms of
Well-
looking at this vis-a-vis some of our higher dimensional problems, Henry, or?
It would probably help you if you had the program. Oh, there was one point I was going to mention, I'll come back to that. All the programs we have to do either the variational method or the Monte Carlo method, you're welcome to. What we have done is we have cast both those problems in terms of an ASCII script file that you fill out
Yeah.
that tells us what the problem is
All right.
and bounds on the search variables.
Yeah.
And we have a Python code that automatically creates the underlying optimization program, the underlying Monte Carlo
All
program.
right. So good.
So at this stage, you have to be able to type and speak English.
Which is possible.
Right, right. Okay, not necessarily in that order.
Yes.
How you would do a huge problem, you'd want to automatize that
Yeah,
in some way.
you'd have to basically.
We'd have to think about that, but maybe the low scale or the smaller scale problems that we talk about would be a guide to how you.
Yeah, that's right. We have actually got people.
But I mean, it is way cool though, I mean, this stuff's just going back, that, you know, if we can go and take some of these problems that end up being, you know, hard to parallelize onto
Yeah.
GPUs and stuff, and if we
We
just
can-
go and say, well, we really don't care about the
Okay.
resolution because we don't have it anyways.
Yeah, yeah.
And if this again allows us to be able to do the data assimilation
It's natural for
with
you.
something that, which will allow us to get around some of the issues of parallelization,
Yeah.
that is, I'd say that's huge.
That would be huge.
Well, you also get out of it the statistics that answer the kind of question.
Oh,
What
yeah,
about
that's
the tail of
everything
the
for,
margin?
that's everything for.
Yeah, it actually couples the. Yeah, it also couples it.
So I wanted to say.
Much more tightly was the assimilation problem.
Right.
So you have it all on that playing on level.
That's right.
Yeah.
It really, if I may
Yeah,
say it,
yeah,
it
yeah.
ties together
Yeah, yeah,
how
yeah.
you use the data and how you use the models that the
Yeah.
data has been
Yeah, yeah.
used for. I wanted to come back to one of Ollie's questions, and that is, our present strategy on how we do the Monte Carlo calculation is to do the variational calculation once, to get a path which is near an extremum of the action, and that's where we start. So we've also start at a random place in a 1,000-dimensional space or 100,000-dimensional space, and eventually Metropolis Hastings gets you there. But it's much, much more efficient and faster if you start near the right answer. So we run these programs variational to get an answer, and that's our starting place for the Monte Carlo. And that seems to work pretty well.
Yeah, well, this tends to be too, I mean, you go and you want to do that linearization and find the particular optimum point and linearize around that, so.
So another way to say it is Metropolis Hastings says, I don't care where you start, I'll get you there. Our way of deciding where to start uses the action, in other words, part of
Yeah,
of
yeah,
the
yeah.
actual dynamics is a place to
I've
start.
never seen a good Metropolis Hastings that doesn't go and understand the linear solution or the stationary phase point. And then you expand about that stationary phase point, and then you go and you then explore the nonlinearities of Metropolis. So,
Anyway, that's how, we got there too, by just
yeah.
screwing around until we got the right answer. What can I say?
Yeah. You know, it's sort of funny, it's a total aside, a little piece of history. Did you ever read, what is they interviewed Marshall not too long before he died, and one of the particular questions had to do with this paper and the authorship on it.
How the hell did he get to be an author? I have no idea.
This
Is it his
is-
idea?
No, well, this is the funny thing, okay, this was done because they were trying to do EOS at Los Alamos, right, in the 50s, right, okay? It turns out that Marshall did all the work in terms of the theory of it, right?
Really?
His wife did all the calculations. Metropolis was the first author because he was the manager of the group that Marshall was in and did absolutely nothing in terms of the development of it, right? And Teller's wife got on it because she wanted to get back in science and Teller convinced Marshall it'd be a good idea to put her name on the paper
But
and
she
start
knew nothing.
building back up her scientific credentials.
That's
So-
astounding. I didn't know that.
I'm sorry, it's just, when I read that, it was like, wow. Because
Did you know Marshall before?
he was one of my advisors, I did a lot of work with
You know,
him.
did you know Marshall Rosenberg?
Yeah.
He was very funny guy, very funny.
Yeah, and I know, if you know Marshall too, he's not the type that he never would take credit for anything. He was
Yeah.
very first person to give credit to other people. And he wouldn't tell a story like that unless it was really true. So,
I once met Marshall, it was at O'Hare Airport. I was going somewhere, he was going somewhere else. And I had gone to give a talk somewhere about why using neutrinos for communication was a really bad idea. And so I was telling Marshall this, and he says, you know, there's another way to think about it. It's a really good idea if you don't have much to say.
Excellent.
Which was exactly Marshall Roosevelt, right? Modest, kind of cheerful.
It's a really good idea.
yeah. But I mean, it's just amazing though, because
That's
you know, it
interesting.
ends up being, you know, the name is Metropolis, but he
That's
had
amazing.
zero to do with the development of it, you know.
I will start referring to it as Rosenberg Hastings.
Yeah.
Because Mr. Hastings did do something in 1970 to organize it better, that's true.
Yeah, no, absolutely.
All right.
Yeah, well, Haley, that was really nice to have that.
So I'm open to, I mean, after you guys talk about how it is you want to do,
Yeah,
to
yeah.
joining in some way or
That'd be
another.
great. That'd be really great.
I mean, that's up to you to decide how you'd like to do that.
That would be most appreciated, because I mean, at the moment, we're really, I think it will fit beautifully. I'm a bit struggling with the degrees of freedom still that we have, but I think it's really a good opportunity to,
Okay.
if you can help us with.
You know, I think that's where too, though, we could also step back and ask really how many degrees of freedom are really in the problem.
Exactly.
Because I have a hunch that it's sort of been blown out.
Yeah.
I mean, 'cause again, for most of the more complicated problems I've worked with, that people keep on advertising 10 to the 6, but
It's
if
really-
you really go and look underneath the covers, it's 10 to the 4.
Yeah. And
In other cases, you know, get down to 10 to the 3rd. So.
yeah.
In other cases, and then, you know, the cases we've had, but, you know, I think with 10 to the 4, you know, for most of the problems I've looked at, so.
Well, I guess, I mean, what we can do in the first instance is actually break down the dimensionality by actually just looking at very large scales.
Mhm.
And then it is actually simplifying the problem quite dramatically.
And also, I mean, right now too, I'm not sure, I mean, are you going and using sort of body fitting coordinates? You're using full finite element, right?
Yeah.
But I mean, you know, how much of that is really for numerical stability versus actual sort of resolution with respect to the measurement, right? And so, I mean, in terms of what you're doing here, or the path that you need to optimize over,
Yeah.
many times I've seen that you can go and strip it down because your real resolution,
Sure, it's
in
not
terms of the physics, is
It's
much more coarser.
much coarser
And-
than what
and
we
then
actually.
and you see that you're throwing these extra zones in
Yeah.
just because of numerical stability
Yeah,
issues.
Yeah,
than we
sure.
do at the forward model.
Well, that's another point where we can gain a lot here, by actually considering uncertainty explicitly.
You could actually make that part of the overall computing strategy,
Yeah.
in some sense coarse grain, solve that
Yeah.
problem.
And then
Use that as your initial guess
initial
for the
guess,
next.
Yeah,
exactly.
it's
And then
it's a
go-
trick
go
we're
down
So
using
you
here.
discover that you're not learning
Exactly.
anymore.
I mean, and also, I mean, because you're talking about, this is sort of time discretization that you're talking about, sort of, I mean,
Space discretization has been put in that index A, it's all
But could we go and also say that because of tolerance, we can also reduce the spatial?
Sure.
Well, the information
Sure.
entropy will give you that value, wouldn't it? Yeah.
This formulation doesn't know how you got to these equations.
Okay.
Truly, in your case, you want temperature and pressure at X, Y, Z,
Mhm.
and T, and all of these guys in their discrete form will all get lumped into there.
Yeah, yeah.
I mean, I've
Hidden
hidden those in order to try to discuss the overall way of looking at it, and now you have to, of course, back that out for your problem.
Excellent. Thank you, Andy.
My pleasure.
Very good.
Yeah. No,
Very
thank you
good.
for teaching me about continuum mechanics.